At 22:15 UTC on June 6, 2026, less than 18 hours ago, NOAA's Space Weather Prediction Center issued a G3 strong geomagnetic storm watch for June 8th, citing the Earth-directed coronal mass ejection that tore away from the Sun on June 6th. Its associated Type 2 radio emission measured at an estimated velocity of 838 kilometers per second, and the fact that this new CME is arriving into a magnetosphere that has not yet fully recovered from the cannibal CME that struck earlier this week. The Sun did not send one eruption. It sent a sequence. And the sequence is not finished. If you rely on this channel for science grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the GOES 19 SUVI instrument operated by NOAA, the European Space Agency's coronagraph records, and peer-reviewed research into solar cycle behavior and geomagnetic storm impacts. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public. The responsibility to check belongs to all of us. But that is not even the complete picture. Because what the G3 watch issued last night represents is not a single event with a clear beginning and a clear end. It is the latest pulse in a sequence that began building on June 2nd, when region 4461 and region 4455, two of the most magnetically unstable sunspot clusters currently crossing the solar disk, each produced M-class flares strong enough to trigger R1 radio blackout conditions across parts of Earth's daylit hemisphere. What followed, across the next 4 days, constitutes one of the most sustained periods of Earth-directed solar violence in the current solar cycle. And what is arriving on June 8th is not the aftermath of that period. It is, by every instrument currently tracking it, the continuation. The Sun has not quieted. It has reloaded. To understand what is actually happening on June 7th, 2026, the day this script is being written, requires understanding what sunspot region AR4455 is. Not just what it did, but what it is. Structurally, magnetically, and in terms of what it represents about the behavior of a star in a specific and relatively rare phase of its 11-year cycle. AR4455 carries what solar physicists classify as an anti-Hale magnetic configuration. That designation is not a technicality. It is, within the science of space weather forecasting, a warning written in the language of magnetic polarity. During any given solar cycle, sunspots form with a consistent magnetic orientation. Leading polarity in one hemisphere, trailing polarity in the other, following a pattern known as Hale's law, named for the astronomer George Ellery Hale, who documented it in the early 20th century. An anti-Hale region violates that pattern. Its magnetic polarity is reversed from what the solar cycle would predict. This reversal creates unusual and intense magnetic shear at the surface of the Sun, an instability that makes the region significantly harder to model and significantly harder to forecast. Standard flare prediction tools are calibrated for normal Hale configuration sunspot regions. Anti-Hale regions fall outside those calibrations. They can, and AR4455 did, produce X-class flares in rapid succession even when preliminary assessments of their complexity suggested a lower threat level. Fewer than 10% of sunspot regions display this reversed polarity configuration. AR445 is one of them. What AR4455 produced on June 3, 2026 must be stated plainly before the scale of it can be understood. At 01:36 UTC, the region fired an M9, 3-class solar flare, a flare powerful enough on its own to produce R2 level radio blackout conditions across Earth's sunlit side, disrupting high-frequency communications over wide portions of Asia, Europe, Africa, and the Pacific. At 07 UTC on the same day, AR445 produced a second eruption, an M7, 7-class flare, whose coronal mass ejection was partially deflected northward by fast solar wind streaming from a nearby coronal hole, but whose Earth-directed component remained confirmed by NOAA's GOES 19 SUVI instrument in coronagraph imagery captured and archived that morning. And then at 11:28 UTC, the same region produced an X1 0-class flare, breaching the X-class threshold that represents the most powerful category of solar eruption the Sun produces. 3 major eruptions, each one launching a coronal mass ejection, each one Earth-directed to a confirmed degree, all within 10 hours of each other. NOAA's Space Weather Prediction Center issued a G3 strong geomagnetic storm watch for June 4th and 5 within hours of the third eruption. Here is what a cannibal CME actually is, in terms the instruments describe: the faster coronal mass ejection, launched by the X1, 0 flare, moved through interplanetary space at a speed that allowed it to overtake the slower ejection from the earlier M-class flares. When a faster CME overtakes a slower one in transit, it does not simply push past it. It engulfs it. The two structures merge. The magnetic fields compress against each other. The plasma densities combine. What arrives at Earth is no longer two separate events separated by hours. It is a single merged structure carrying the energy of both, with a tangled and complex magnetic geometry that makes predicting the intensity of the resulting geomagnetic storm significantly more difficult than forecasting a clean, single CME impact. NASA researchers describe these merged structures as complex ejecta. The key variable, the one that determines whether Earth's magnetosphere sustains a G2 moderate disturbance or a G4 severe one, is the orientation of the magnetic field embedded in the incoming plasma. Specifically, whether the Bazide component, the north-south component of the interplanetary magnetic field, points southward on arrival. When Bez points south, it aligns anti-parallel with Earth's northward-pointing magnetic field, and that alignment opens a doorway. The magnetosphere couples with the incoming solar wind. Energy pours in, geomagnetic currents surge, the storm strengthens. The cannibal CME, produced by AR4455, arrived at Earth's L1 monitoring point. The gravitational balance between the Sun and Earth, approximately 1. 5 million kilometers from Earth's surface, at approximately 0430 UTC on June 6th, marked by an abrupt jump in solar wind speed recorded by instruments stationed there. The full impact was complex. The Bez component initially pointed northward, keeping the magnetosphere partially shielded. But later in the day, solar wind data showed a secondary speed increase to approximately 650 kilometers per second, accompanied by a southward BZ dip, reaching a maximum of negative 17 nanoteslas. That is the number that matters. Negative 17 nanoteslas of southward Bez is not a minor perturbation. It is the kind of reading that produces genuine coupling between the solar wind and Earth's magnetic field, the kind that drives aurora displays visible far from the poles, the kind that NOAA's Space Weather Prediction Center confirmed by reporting that G2 geomagnetic storm conditions were reached on June 5th at 1736 UTC, moderate, not extreme. But the sequence was not complete, because on June 6, 2026, while the cannibal CME disturbance was still moving through Earth's magnetosphere, region AR4461, located in the southeast quadrant of the solar disk, produced an M1, 8-class flare at 1401 UTC. The event was associated with a filament eruption. A partial halo coronal mass ejection was observed in LASCO C2 coronagraph imagery at 1401 UTC. The Type 2 radio emission generated by the event was measured at an estimated velocity of 838 kilometers per second. Fast enough and Earth-directed enough that NOAA's Space Weather Prediction Center issued a new G3 strong geomagnetic storm watch at 22:15 UTC on June 6th for the anticipated CME arrival around midday UTC on June 8th. A G2 moderate geomagnetic storm watch was simultaneously issued for June 9th, as storming is expected to persist into the early part of that day. The 3-day forecast from Space Weather Live, issued at 12:30 UTC on June 7th, today, places the peak 3-hour KP index for this forecast period at 7. 0, corresponding to G3 conditions, during the 18 hours to 21 Osta UTC window on June 8th. That KP index of 7, expressed in the language of what it actually means. Earth's magnetosphere will be compressing under sustained solar wind pressure, geomagnetically induced currents will be flowing through buried infrastructure, and aurora displays will be visible across latitudes that normally never see them, as far south as Illinois and Oregon, under favorable viewing conditions. Think carefully about what the people living in those latitudes experience when they look up and see aurora where there should be none. It is beautiful, it is alarming, and it is a visual symptom of something happening to Earth's magnetic environment that has consequences they cannot see with the naked eye. In the city of Chicago, Illinois, a metropolitan area of nearly 9 million people, the electrical grid operates through transmission lines that run for hundreds of kilometers through magnetically sensitive geology. Geomagnetically induced currents, the ground-level electrical signatures of geomagnetic storms, do not announce themselves with visible light. They flow through pipelines. They flow through railway signaling systems. They accumulate in transformer windings. A G3 storm does not guarantee transformer failure, but it does guarantee transformer stress. And transformer stress in aging infrastructure is not a theoretical risk. It is a documented one. This is not a hypothesis. This is documented in the geological and technological record. On March 13th, 1989, a geomagnetic storm rated G5, the highest level on the NOAA scale, struck Earth following a series of powerful solar flares and coronal mass ejections from active sunspot region 5395. The storm produced a KP index of 9, It induced currents so powerful in the Hydro-Quebec power grid in the Canadian province of Quebec that the system collapsed within 90 seconds of the storm's onset. 6 million people lost electrical power. The blackout lasted approximately 9 hours. Transformer damage was reported across parts of the northeastern United States. Satellites in low Earth orbit experienced increased atmospheric drag due to the heating and expansion of the upper atmosphere under geomagnetic storm conditions. The New Jersey Transit Railway system reported communication disruptions, and that was 1989. The grid has grown larger, the satellite constellations denser, the GNSS-dependent infrastructure, navigation, timing signals, financial transaction systems, more deeply embedded in daily life than it was 37 years ago. The question is not whether a G3 or a stronger storm can produce real-world infrastructure disruption. The 1989 record answers that question definitively. The question that remains open, the one that NOAA engineers and grid operators are working with right now on June 7th, 2026, is whether the June 8th CME arrives with a sustained southward BZ, and whether a magnetosphere that has not fully recovered from the June 4-6 cannibal CME disturbance is more or less vulnerable to what arrives next. Consider also what is happening on the surface of the sun at this precise moment, because it bears directly on the answer to that question. As of the 3-day forecast issued today, June 7th, 3 active regions are actively contributing to the current solar threat picture: AR4455, AR4458, and AR4462. AR4458 has developed a new beta-delta magnetic configuration. The designation beta-delta means that the region contains a sunspot with both positive and negative magnetic polarities within the same penumbral boundary, the configuration most strongly associated with X-class flare production. AR4456 maintains a beta-gamma configuration. X-class flare probability for the current period is assessed at 10%. M-class flare odds hold at 50%. These are not low numbers. 50% M-class flare probability on a day when Earth's magnetosphere is already conditioning itself for the arrival of a fresh CME on June 8th means that the threat picture is not static. It is accumulating. The system is not inactive. It is accumulating. This is precisely what makes the current solar episode significant beyond its individual events. The Sun entered solar cycle 25 in December 2019 by official NOAA reckoning. The cycle's predicted solar maximum, the period of peak sunspot activity, peak flare frequency, peak CME production, was initially forecast for around 2025. Preliminary evidence from NOAA and NASA's solar cycle 25 prediction panel indicated that the cycle was tracking stronger than predicted. What followed through 2024 confirmed that assessment. In May 2024, a G5 extreme geomagnetic storm, the first G5 event since the Halloween storms of October and November 2003, struck Earth following a series of X-class flares from active region 13664. The KP index reached 9. The DST index, a measure of ring current intensity in the inner magnetosphere, reached negative 412 nanoteslas. Aurora were observed from locations that had never recorded them in modern history. The storm was the most intense since 2003. The world's technological infrastructure was more exposed than it had been in 2003, and the storm passed without catastrophic cascading failure, though not without incident. Satellite operators reported temporary communications disruptions. Elevated radiation levels were measured, and the cycle did not end there. Following the May 2024 G5 event, the Sun entered what researchers studying solar cycle 25 have documented as a post-maximum phase marked by increasing production of anti-hail sunspot regions, coronal holes, and filament eruptions, a phase some solar physicists describe informally as the battle zone of the solar cycle, where the Sun's newly flipped magnetic field creates instabilities that drive a second surge of intense space weather activity even as the cycle moves past its technical peak. AR4455, with its confirmed anti-hail configuration, its rapid production of M9, 3, M7, 7, and X1, 0 flares within a single 10-hour window, and its role in producing the cannibal CME that struck Earth on June 4-6. That region is a textbook product of this post-maximum instability phase. The Sun's behavior over the past 10 days is not anomalous within that framework. It is, in the language of the data, consistent with what a star in this specific phase of its magnetic cycle does. This matters for the people who live where this story reaches the ground. Not in the abstract language of KP indices and nanotesla measurements, but in the immediate physical reality of daily life. In Tromsø, Norway, a city of approximately 76,000 people sitting at nearly 70 degrees north latitude, the aurora is a seasonal companion. Power engineers there operate grid infrastructure designed to accommodate geomagnetically induced current events because they know the aurora is not merely a spectacle, it is a diagnostic signal from the magnetosphere above them. But consider instead the residents of northern Indiana, where approximately 3 million people live across communities whose grid infrastructure was not designed with recurring G3 geomagnetic conditions in mind, where the transformer stock is aging, and where the average resident, if asked on the morning of June 7th what a coronal mass ejection is, would not have an answer. They would look at the sky on the night of June 8th and see something beautiful, possibly for the first time in their lives. They would not see the induced currents that might be flowing through the pipelines under their streets at that exact moment. They would not know that GPS timing signals used by the financial systems processing their transactions could be experiencing degradation. The beauty and the hazard are simultaneous. The aurora and the infrastructure risk are the same event. The connection between what is happening in space and what happens on Earth's surface is not metaphorical. It runs through physics. Coronal mass ejections compress Earth's magnetosphere on the sunlit side, extending it on the night side. The compression drives ring currents, loops of charged particles trapped in the inner magnetosphere that flow westward around the planet. These ring currents produce magnetic field perturbations at Earth's surface. Those perturbations induce voltages in any conductor that runs for significant distances parallel to the surface: pipelines, railway tracks, power transmission lines. The longer the conductor, the greater the induced voltage. The United States operates some of the longest high-voltage transmission lines of any grid system in the world. Geomagnetically induced currents in those lines do not trip breakers in the way that a simple overcurrent event would. They appear as quasi-DC, direct current, signals riding on alternating current infrastructure that was not built to handle them. Transformers, particularly large high-voltage ones, can saturate. A saturated transformer produces harmonic currents, generates heat, and in prolonged saturation can sustain internal damage that is not immediately apparent but shortens operating life dramatically. Replacement of large high-voltage transformers, the kind that sit at the center of regional electrical infrastructure, takes months to years and costs millions of dollars per unit. The United States had this conversation formally after a 1989 lesson, and again after 2003, and again after 2024. The systems that came online as a result of those conversations are better than what existed before them. They are not perfect. What NOAA's Space Weather Prediction Center is tracking in real time on June 7th, 2026, is the solar wind flow from L1 monitoring, waiting for the signature that will confirm the June 6th CME has arrived. Pre-arrival conditions were characterized this morning as quiet to unsettled, with the cannibal CME influence from earlier in the week continuing to fade. Solar wind speeds are expected to return toward background levels through June 7th, which means the magnetosphere will have a brief window of relative calm before the June 8th arrival. Whether that window represents a recovery period or simply a pause depends on variables. The instruments at L1 will only resolve when the CME's leading shock actually crosses the monitoring point. The critical unknown is BZ orientation. If the embedded magnetic field in the arriving CME points southward for a sustained period, hours, not minutes, the storm escalates. If it points northward, the magnetosphere shields itself more effectively, and the storm remains closer to the G1 to G2 range. Scientists choose their language carefully here, and that careful language is itself the warning. The forecast says G3 is possible. It does not say G3 is certain. The difference between possible and certain in space weather forecasting with current instruments is the BZ. And Bs cannot be predicted with reliability until the CME is essentially at Earth's doorstep, roughly 30 to 60 minutes before impact. 30 to 60 minutes. That is the current operational lead time for the most consequential variable in geomagnetic storm forecasting. 30 to 60 minutes between the moment when grid operators know with certainty how severe the incoming storm will be and the moment when that storm begins imposing itself on the infrastructure they are responsible for protecting. This is not a failure of modern science. It is an honest statement of where the science currently stands. NOAA's Deep Space Climate Observatory, positioned at L1, provides real-time solar wind monitoring that represents the state of the art. It is remarkable technology doing exactly what it was built to do. And the margin it provides, 30 to 60 minutes, is real and has value. Grid operators who receive that warning and act on it, switching protective protocols into place, can reduce transformer saturation risk meaningfully in that window. The question is whether those protocols exist, whether they are current, whether they are practiced, and whether the operators responsible for them are monitoring space weather data on the evening of June 8th as attentively as they would if a hurricane with 36 hours of advance warning were bearing down on their service territory. Geomagnetic storms offer no landfall imagery. They produce no visible wall of clouds approaching from the coast. They arrive in data streams and magnetic measurements from a point 1, 5 million kilometers away, and the people most affected by them are often the last to know they're coming. Here is where this account becomes genuinely significant beyond the scale of any individual storm. The Sun has been producing anti-hail sunspot regions with increasing frequency in the period following the May 2024 G5 event. Region 4455 is not the first such region in this sequence and is unlikely to be the last. The solar cycle does not simply switch off after its maximum. It redistributes its energy into a different and in some ways more unpredictable pattern. The fact that AR4461 produced another Earth-directed CME on June 6th at 838 kilometers per second, while the effects of the AR4455 cannibal CME were still moving through the magnetosphere, is not a coincidence of bad timing. It is what a sun in its post-maximum phase does. Multiple active regions, multiple flare sequences, multiple overlapping CME arrivals that challenge models built around clean, single-event scenarios. The instruments are showing this. The archive of events from the past 4 years is documenting it. The pattern is not hiding. The Carrington event of September 2, 1859, named for the British astronomer Richard Carrington, who observed and documented the solar flare associated with it, remains the largest geomagnetic storm in recorded human history. Telegraph systems across North America and Europe failed. Some operators reported receiving electric shocks through their equipment. Telegraph paper caught fire at some stations from the discharge of induced currents. The storm's DST index, reconstructed from historical magnetometer records, is estimated to have reached negative 850 nanoteslas. For comparison, the May 2024 G5 storm reached negative 412. The Carrington event was, by any metric, roughly twice as powerful as the strongest storm of the modern satellite era. The infrastructure of 1859, telegraph wires, that was essentially the full extent of it, could not carry the implications that the same storm would carry today. A Carrington-scale event striking Earth's current infrastructure is a scenario that NASA, FEMA, the UK's National Risk Register, and multiple European space agencies have modeled formally. The models do not produce reassuring results. They are not meant to. They are meant to motivate preparation. The June 2026 sequence, AR4455's triple flare cannibal CME, the G2 storm that resulted, and now the June 6th CME from AR4461 with its G3 watch for June 8th, is not a Carrington event. It is important to say that clearly. The KP index forecast peak of 7 for June 8 is a strong storm by any modern standard, but it sits at G3 on a scale that ends at G5. The infrastructure stress it represents is real, the disruption potential is real, and the monitoring it demands is real. But this is not the scenario the modelers at NASA and FEMA have spent years gaming out. What this week represents instead is something else. It is the accumulating evidence that the Sun, in its current phase, is capable of producing these events in rapid succession, in overlapping windows, with insufficient time between them for full magnetospheric recovery from active regions whose anti-hail configurations make them harder to forecast using standard methods. It is the demonstration, in real data from real instruments in June 2026, that the question the planetary risk community has been asking for 20 years is not merely theoretical. The question is not whether, the question is when. There are 340,000 people living in the metropolitan area of Duluth, Minnesota, sitting at approximately 46 degrees north latitude, far enough south that a G3 storm would deliver aurora directly overhead. Some of them are reading about tonight's potential display on their phones right now. Some of them are planning to drive to the lakeshore after dark and watch. They are doing something entirely reasonable, entirely human, seeking out a moment of planetary beauty in an ordinary week. What they may not know, and what the data on June 7th, 2026 actually shows, is that the same process producing that beauty is simultaneously running currents through the pipelines beneath their city, slightly degrading the GPS signal their vehicles use for navigation, and placing stress on the electrical infrastructure that will wake them up in the morning with heat and light and the ability to charge the devices they carry everywhere. The aurora and the infrastructure risk are not different stories. They are the same story. They always have been. The 3-day forecast period ending June 9th will not be the last time this statement is accurate. AR4456 maintains a beta-gamma configuration and gained additional magnetic complexity on June 6th, including a weak delta signature in its intermediate area, according to SWPC forecasters. New spot formation was observed north of region 4462 on June 7th, pending formal number designation. AR4458's confirmed beta-delta configuration makes it the top candidate for additional major eruption events in the coming days. M-class flare probability remains at 50%. X-class probability sits at 10%. The active disk is not emptying, it is restocking. There's a line that space weather scientists at NOAA and NASA use when the instruments are showing what they are showing on June 7th, 2026. They say, the monitoring is in place and detection is possible, but prediction is not. They say it calmly because they have read enough data to understand what calm professionalism requires. What they mean by that sentence? the full weight of what they mean, is that all the instruments humanity has placed between itself and the sun are doing their jobs with extraordinary precision, and that the 30 to 60 minute warning window they provide is genuinely valuable. And that prediction of CME magnetic orientation before arrival remains beyond the reach of current models despite decades of effort to extend it. They are not apologizing. They are being accurate. And accuracy here is the only honest response. The CME that left the sun on June 6 at 1401 UTC, first observed in LASCO coronagraph imagery at that same time, is currently traveling through interplanetary space toward Earth at an estimated velocity derived from its associated Type 2 radio emission of 838 kilometers per second. It will reach the vicinity of Earth on June 8th. What it carries in its embedded magnetic field, whether the BIS component points north or south, how long it sustains that orientation, how the compressed magnetosphere of a planet that has just endured a cannibal CME impact responds to a second major arrival, those answers exist right now in the solar wind between the Sun and Earth. The instruments will read them when the CME arrives at L1, not before. The rock beneath every city on the sunlit side of Earth on June 8th was formed over hundreds of millions of years by processes that the sun drove and continues to drive. The same stellar energy that produced the solar wind shaped the magnetic field that surrounds this planet and periodically sends billion-ton clouds of magnetized plasma racing across 150 million kilometers at velocities that compress the boundary of the magnetosphere until it sits closer to Earth than some of the satellites we depend on for daily communication. The star has been doing this for 6 billion years. The magnetic storms and the solar flares and the coronal mass ejections and the geomagnetically induced currents and the aurora, all of it, happened long before there were instruments to measure it, long before there were telegraph wires to catch fire from it, long before there were transformers to saturate or satellites to drag or navigation systems to degrade. What changed is not the sun. What changed is what we built in its path, and how thoroughly we have forgotten in the daily rhythms of modern infrastructure that the path was never ours alone to occupy. The watch for June 8th stands. The CME is in transit, and somewhere between the sun and Earth, moving at 838 kilometers per second through the interplanetary medium, the answer to the question the instruments cannot yet read is already decided, embedded in a magnetic field orientation that will announce itself with approximately 30 to 60 minutes of warning at the L1 monitoring point between one world and the star it orbits.